Have you ever been playing a game or running an application for a few hours and it seems noticeably slower than when you first opened it? Well, that's probably caused by something called a memory leak. When a software wants to declare a new variable, it has to go to the RAM and physically allocate new space for that variable. However, sometimes you no longer need that variable, and if not properly deallocated, that variable will stay in memory hogging up resources. And this continued process of creating and never deleting variables can cause noticeable slowdown in the application as resources become more limited. High-level languages such as GDScript typically have something known as garbage collection, which means that the language automatically identifies and frees memory that is no longer needed. However, there are times where this mechanism can fail. Garbage collection is never perfect, and there are a few spots that you as a programmer will need to check over to make sure that there is no leakage. The main area where you may encounter memory leaks in Godot is when declaring a variable that holds a resource or a node. For example, here I have a custom resource, it's just called test resource, and it can hold a number and also a reference to another resource. We'll worry about this more in a bit. In Godot, we have something called a reference counter. Essentially, every time we reference this resource, its reference count will go up. So right now, it's at 1. And you can check this by typing print new resource.get reference count. And if we run this, you see that reference count is 1. And if we reference it again, let's say we create a variable called copy new resource. This will be a copy of our new resource. Assign it to be our new resource. Now the count will go up to 2. After using your resource, your goal is to get its reference count back down to 0. Otherwise, if it's above that, it will be sticking around in memory hogging up resources. Since we created and declared these variables with inside a function, after we're outside the function, the engine will automatically free these variables. Now, remember from before where I said that our resource has a variable that can hold another resource? Well, here I have an example of creating two resources and having each resource reference each other. So when we first create our resource 1, its counter will go up by 1. When we create our resource 2, its counter will also go up to 1. Now here, we're referencing resource 2. So resource 2, which is this one, will go up to 2 in its reference counter. And then resource 1, which is this resource, will also go up to 2 when referencing it here. However, once we leave this function, we're going to encounter a strange issue. These resources will be accounted for, and they will be disposed of properly. However, these references get trapped in a cyclical reference state that is inaccessible outside of this function, which, you guessed it, is a memory leak. The way to prevent this is by using something called a weak reference. Essentially, instead of creating a full-on reference to our resource, we can use a weak reference to reference it in our other resource. And since this is no longer a full-on reference, this count will actually be at 1. And so when we leave this function, our references will be accounted for. However, since weak reference is a much more limited reference, we can't do things such as print resource 1 dot other resource dot test num, which would get the resource 2 test number, which should be 27. We will get an error if we run this. We have to first turn this into a full reference. So to do this, we type in dot get reference in between the other resource and the test number because the other resource is the weak reference. And now if we run this, we will get the expected result, that is 27. But doesn't this cause the same problem because you've still created a full-on reference to the other resource? Actually, no, because when we call getReference, we're not actually altering the other resource itself, which is still a weak reference. This is a fully self-contained reference that gets disposed of after running this line. Another thing that causes memory leaks is something called an orphan node. This can be caused by improperly removing the child from the parent or the parent dying in a car accident. For example, here I have a preloaded test node, of which I am instantiating. And as of this line, this is just an instance and it has not yet been assigned to a parent, so it's an orphan. However, I have a test node inside my scene tree that I'm also referencing, and when I assign the instance as a child to that test node, it will no longer be an orphan. You may have noticed that I have a custom function here that checks for orphans. Let's go to open that up. Here, I have a simple orphan count variable that gets the total orphans using the performance monitor, and if that count is greater than 0, we'll be printing out that orphans have been detected, and we'll be running the built-in function that will print all the orphan nodes. You can check that out here. I'm also using another built-in function called printTreePretty that will print out the entire scene tree so we can ensure everything looks correct as we go. So as of this one, we're all good, our instance is not an orphan and we have everything accounted for. However, if we then run the remove child function on the test node, the instance will become an orphan again. And the key thing you need to remember is orphans do not automatically get freed. So if we want to remove it as a child but also delete it, we can simply just run instance.queue_free, which will delete the instance and delete it from memory. Anyways guys, if you have any questions or comments, please leave them down below and don't forget to like and subscribe. Thank you!